about mean field version of Bank and El-Khoury's representation of Jurassic processes, please.
Okay, thanks very much for the invitation. It's a great pleasure to talk about my work in this probability seminar. So this work is a joint work with Zhou Jun, a colleague at Chinese University of Hong Kong, and also our PhD student, Xiaolu Tan. So we're going to talk about this the Bank El-Khoury representation for stochastic processes, and we provide a mean field extension, and I'm going to talk about some application of this mean field extension of this representation theorem. Okay, so the main motivation and the application of this extension is from the mean field game. So for this reason, I want to start my introduction with the mean field game. Okay, so mean field game is a symmetric differential game with a very large population. And in this game, so first we consider a finite number of agents in this population, and each agent solve optimal control problem. Okay, just the control. So each agent have an independent Brown motion, this noise, and the control process is alpha. We control the district, this one, and the objective is to maximize this reward function. Okay, so this reward function depends on the underlying process X and also the control process alpha. And most importantly, it depends on this interaction term. So this is the empirical measure induced by the state of all the other agents in the population. Okay, so this is symmetric. So M can be considered as an environment induced by the whole population, the optimal behavior of the whole population. Okay, so then the objective is to find the equilibrium of the Nash equilibrium to this game. This is a game. Okay, so but the mean field game, the idea is to consider the limited case when the number of agents goes to infinity, and when the number of agents goes to infinity, and because of the symmetric, because the Wi is just independent Brown motion for every agent for every I. And in this case, formally, we can consider this empirical distribution induced by the state of every agent just leads to the distribution of a representative agent. Okay, so this is M in the limited case. We take a representative agent, and this interaction term, also mean field term, is the law of the representative agent. Okay, and so for this representative agent, the problem is to solve this optimal control problem, and the interaction becomes this MT. Okay, so this idea, so this is a coupled system, because to solve this optimal control problem, we need to know what is M. Okay, but M depends on the optimal control of M. So the law of alpha, X alpha star. So this is the optimal behavior of the agent. Okay, so this is a coupled system, and we can also consider it as a fixed point problem. Okay, so we give an M. So given M, we can solve this optimal control problem. We can obtain alpha star, and then with this alpha star, it induces another M, and we hope that the induced X alpha star, the induced measure, is this initial given M. So this is a fixed point problem. Okay, at the very beginning, so this problem has been introduced initially by this PDE formulation. So we usually use the Bellman equation to characterize the optimal control problem, and also, so this is actually the Hamiltonian, And we also use the Fokker-Planck equation to characterize the marginal distribution of this optimal, with this optimal control. We can characterize the distribution of X star. Okay, so this problem has been initially introduced by Lasky-Lyons and Huang, Malham and Keynes some years ago. And the most basic question in this story is to find the existence uniqueness, and also because this is the limit behavior of a very large population, so we want to also find the limit theory to show that this consists of the limit of a finite number, a finite population game. Okay, and also the stability numerical method, and also the associated master equation is there. Some popular problems in this story in the MIFI game. Okay, and also there is some variations. Okay, so after this very initial formulation, there is some variations of the MIFI game. So for example, for the MIFI game with common noise, so imagine, so in the initial formulation, every agent has an independent Brownian motion Wi. Okay, and now we introduce, we can consider the case with a common noise Brownian motion, so common noise B. And in this case, the B is the same for every agent, for every I. And in this case, for by very formal law of large number, and we can see that the empirical distribution will convergence to the conditional distribution of the X star law in the common noise. Okay, so this will lead to a MIFI game with common noise. Okay, another variation of this one is, we can say, so at the very beginning, at the initial formulation of the MIFI game, we consider the every agent solve optimal control problems. Okay, so this is optimal control problem. Okay, and we can replace this optimal control problem by an optimal stopping problem. Okay, so this is optimal, we can call, so this is so-called MIFI game of timing. So in this one, every agent in this game solve the optimal stopping problem, for example, and in this case, the interaction term will be the distribution of the optimal stopping time. Okay, so for example, this is just one example of interaction. Okay, and so this problem we can refer to the paper of Newts, Carmona, De La Rue, and Leca. And Bertucci used the PD arguments to study also, and also the recent work of more recent work of Bourlet and Dmitrievsk and Tankov. Okay, and also you can consider another, if we change this the classical or more standard stochastic optimal control problem to a singular control. So a singular control problem is that classical or more standard formulation of stochastic control, we just control this process alpha here. And for singular control, you can consider an increasing, adaptive increasing process. And so this process, Xi could have some jumpers. Okay, so in this formulation, whatever the value of alpha, there's no jumper of the process X. But with this Xi, you could have some jumpers in this one. And usually this is called a singular control. Okay, and in this case, you can consider the joint distribution of the controlled process and also this jumper process Xi. Okay, so for example, Fu and Hurst and more people, okay, also study this variations of MIFI game. Okay. Okay, so I just finished my my very brief introduction to the MIFI game. Okay, so in this work we want to study a MIFI version of the representation theorem introduced by Peter Bank and Nicole Elegari about 20 years ago. Okay, so in this classical theorem, this is a very general theorem. So let me consider a very special case. Okay, so there's too many conditions. So maybe we can consider F is the identity F of L. So F it could depend on T and omega. Maybe we can forget this T omega at this moment. Okay, so we can consider the case F. Sorry. So we can consider this case F of L just equals to L. This is identity function. Okay, so this is a very simple example. So the result, so it satisfies all this. So if F equals to L, then of course satisfy all the technical condition. Okay, and the theorem says that for every optional process Y in the class D is some integrability condition and also some continuity in expectation, upside continuous in expectation. Okay, this T, capital T, it could be finite and also could be infinite. It could be finite or infinite. Okay, but the last term is 0. It's not necessarily 0. It is, if it is integrability, integrable random variable, and you can always add, in fact, you can always write a martingale. So you can always add a martingale here, and then because this is conditional expectation, and it doesn't change the representation. So without the loss of generality, you can assume that the last value is 0. Okay. So for
this is optional process in class D.
Yes. So yes, in class D. So if your final value is integral random variable, okay, you can take the conditional expectation, and this leads to a difference of martingale. Okay. So this condition is just not very important. This is not important. And in this case, there you can find the optional process L. So now F is identity function. In this case, you just forget. I write X here. So this process X is omega. Okay, actually, I prefer write X to say that there is. So imagine this is canonical space. So X is omega. Okay. So I prefer to write this because in the mean-free term, I want to write law of X later. Okay. So for the moment, this is just this theorem. Okay. So if we look at this representation, we see that for every tau, of course, we can find for every tau, it's easy to find a process L such that Y tau equals to this expectation. But what is not trivial is that this L, okay, for every tau, this process L is universal. You can find a universal process L such that this is super from tau to S. This is super from tau to S and the ds. Okay, and of course
it was X. What is X?
X is omega. X is omega. I prefer, okay, in the initial formulation is you don't need to write X, but I prefer to write X because in the mean-free term, I want to write X as law of X. I want to, this is underlying process. So imagine that X is omega. Imagine that is canonical space and this X of omega equals to omega.
Thank you.
Okay. Okay, so this is even in the deterministic. Okay, so imagine the deterministic setting. So there's no expectation, there's no conditional expectation. Just giving you a function of t, a deterministic function of t, and then you want to represent this a function of t as an integral of ds with this super, and this is not trivial. It's not so trivial. Okay. Okay, so this such a representation theorem has many applications. I want to just mention it can be applied to solve a singular control problem, and can be solved for optimal consumption problem studied by in the paper by Bank and Reader. And also another optimal stopping problem. I want to present a little more on this optimal stopping problem. Okay, so imagine that you consider this optimal. So in this representation system, we are given y, and we have f, we have the function f. We're given for every y, we can represent by l, by this l. Okay, so with this y and f, let's consider this optimal stopping problem. So we want to stop tau here and y tau here. Okay, and then for this heating time, so we can do the representation and we can find an optional process L. And the first heating time of the level L is the solution of this optimal stopping problem. Okay, and what is amazing is that in fact this L is universal. So for if you change this L, it doesn't change. It changes the optimal stopping problem, but with the same process capital L, the heating time provides the optimal solution for this. So somehow the same process L provides a universal signal to different optimal stopping problem. Okay, so you just take the same process L and you solve a family of optimal stopping problem. Okay, so this is the a very powerful application of this representation theorem. Okay, so first we have noticed this theorem, and so last year we have working on this. We have used this theorem to do a principal agent problem. So to design a contract, okay, a universal contract, design some Y for different agents, and to do optimal contract design problem. So okay, so we have found this application in your previous work, and this is also why we have interested to this representation theorem, and we want to do some other extensions of this one. Okay, just to mention before I talk with our MIFID extension, I just want to mention that such a representation theorem has some other extensions for variant of the reflected BSD by Jima and Wang, and also recently, so also the Peter Bank has extended this representation if this process is just the Meyer or sigma field measurable. Okay, and also the DT, you can replace this DT by some random measure mu, which have atoms. Okay, so you can have, so this is DT, you can replace this DT by mu of DT when it is no atom, you can make this extension. And what is not trivial is this, you can consider some measure has atoms in this extension. Okay. And for the proof of this one is very close to the Gittins index theory and related to some other works by Eligari and Karazas. Okay. Okay. So now, so we take this one. Okay, we take this representation theorem. Okay, and we just introduce a MIFID term. Okay, so just we want to say, okay, so let's look, we have this nice representation theorem, and how about, so somehow just for, I don't know, we don't have any motivation, we just say, okay, let's do the MIFID game or the MIFID control or the MIFID problem seems quite popular recently. So we just say, okay, let's add a MIFID term in this representation theorem and how to see what it happens. Okay, so this is very just by curious, we add a law of L in this generator function x 5. Okay, so but later we can consider f of law of x, the joint law of x and L. Okay, so this is also the law of. So later we will consider this law of x, joint law of XL, because we can consider interaction and we want to consider x as my underlying process, and I hope that I have some joint distribution of this x and L. Okay, so now the question, this MIFID, the extension of the representation theorem says that if we have this law of L in the generator function, can we still find optional process L? Okay, can we still have this optional process L? Okay, so later we realized this could be a fixed point problem. This could be a fixed point problem. Okay, so because we can consider it as a fixed point theorem. Okay, so problem. This is also why we try to prove to obtain existence and uniqueness result for this representation. Okay, so this is a fixed point because if we fix law of L as M1, okay, as just a fixed giving just replace this by M1. Okay, so this is input as an input. So then now this we have standard. So M1 is fixed. So this is now the classical Bank-Eligahui representation. Okay, so we can find some process L. So let's say denoted by L tilde. Okay, this is L tilde to represent this process Y. Okay, and now the Y L tilde induce the law of L tilde induce a new measure M2. Okay, so as an input M1, we have output M2, and we hope that this M1 equals to M2. Okay, so this we consider this mapper as a fixed point problem. Okay. Okay, and then we can realize we want to find some motivations to this mean field extension. So this is an extension of the classical problem, and we realize that in fact we can apply this to the mean field game of timing, So just to take an example. Okay, so we consider a very mean field game of timing with multiple population. Okay, so in each population we have infinite number of agents, but we have different many population. Okay, in fact we have infinite number of population in this mean field game. Okay, so in this one, in the population L, so the population are indexed by L. Okay, so in the population L, we take a representative agent. Okay, we take a representation agent. Okay, then this representation agent solve this optimal control problem, given the interaction. Okay, so mu is the interaction. Mu is the environment. So we solve this optimal control problem. Okay. And then the idea, in this case, the mean field game of timing will be, we hope that to find a fixed point. If we find a tau star, and the interaction mu will be the law of tau star. Okay. So in the previous, in the idea of the mean field game of timing. So, okay. But here, because we have different population indexed by L, we want to find the joint distribution of the stopping time of each population, okay, of all population. So now that we should consider intuitively, we should consider the law of the joint distribution of the optimal stopping times of each population, and this can be considered as an environment induced by all the agents in all populations. Okay, and the idea, okay, the solution equilibrium or Nash equilibrium in this mean field game is just a couple of tau star and mu, such that tau star is the optimal solution to this one, and the mu is the distribution induced by the optimal stopping time for every agent. Okay, so this is an extension of the mean field game of timing studied in the previous literature to the multiple population situation, Okay, and our remark is that our observation is that in fact, if we remember, this optimal stopping problem can be solved by the heating time of the process L. By the process capital L. So remember in this application, okay, in this application of this one, for different L, the solution of this optimal stopping time is given by the universal optional process L. So the heating time of this process to the level L gives the solution of this optimal stopping problem. Okay, so in this case, if we solve this mean field representation problem, and the law of L, the law of the process L, will induce, if we know the process of L, and we know the process of the heating time, the joint distribution, okay, we can obtain the joint distribution of all heating times. Okay, so this is the same process induced the optimal solution of difference. So the law of L induced the law of the optimal stopping times. Okay, and in this case, so at least formally, we can say we can obtain this one, given a solution to the mean field representation, and then we can deduce a solution to the mean field game of time with multiple population, and the solution is just this the heating times of this process L, and the induced distribution is just induced the joint distribution of the heating times Okay, there is I just want to remark this is a strong solution. Okay, because in this story we fix probability measure, we fix the filtration, we fix the probability space, we fix the filtration. So we find this. So in this one, we fix the filtration, and we find this representation. So somehow, in this sense, this is a strong solution to the mean field game of time. I just want to mention that because in the literature, people need to relax. Okay, usually you need to relax this to find a weak solution to the mean field game, to very existence. Okay. Okay, and also I will not present this in details. I want just to mention that we can also, because of the representation theorem, can be applied to different optimization problems, to the optimal stopping, to the singular control, to the optimal consumption problems, etc. And then we can, so in particular, or if we find mean field representation of stochastic processes, in fact, we provide a universal approach to study different mean field game problems. And in fact, this mean field game problems have been studied individually by different approaches. So somehow this could provide a unified approach to study different problems. Okay. And also in our previous work, we consider this the exit contract design problem or principal agent problem. We can also extend this principal agent problem to the mean field game setting with this by this mean field extension. Okay, so another application. Okay, but this is not done. Okay, this is maybe. We can expect, okay, and I think we can naturally expect such application to the exit contract design problem in the mean field game setting. Okay, I just want to mention that in the mean field game setting, there is also the planning problem introduced by Lyons. So this is kind of also of a principal agent problem in the mean field game setting. Okay, so finally, in fact, motivated by its applications to the mean field game, and in fact, we are going to consider a more general formulation of this extension. So more general formulation is that we're going to consider an interaction which is more complex. So our interaction is M, we're going to consider a common noise setting. Okay, so we have a common noise G, and so the interaction will be the distribution of my X. So X will be the underlying process, and the L, the representation process L, and the conditional law of this X and L. the conditional. We're going to consider the conditional law of X and L. So this is the first point. And the second point is that we are going to let Y, the process depend on this measure. So usually this Y depends on M is a function of the XM. So in fact, for example, XM is a diffusion process with parameter depends on this measure. Okay, so Y is generally is a function of X. So in practice, in application, so Y, the reward function, for example, Y is a reward function in the optimal stopping problem, and F is also a reward function. The parameter is a function of, sorry, this typo here. So it depends on M, but in practice, it depends on XM. So this is why we prefer to use the joint law, the joint conditional distribution of XM and L. And another one is that we don't really consider the distribution of L. We consider the distribution of L hat. So L hat is the running maximum of L. And there we consider this case, we consider this joint distribution for two examples, for two reasons. The first reason is that we need some, okay, so in general, this process L here is just the optional process, doesn't have any regularity. Okay, so if we consider the law of L, it will be the distribution of, so it will be a distribution of this some process R. Okay, so it's very difficult to find a good topological structure for this space. Okay, and so if we consider the running maximum, we know that it's increasing process. Okay, so for increasing process, it has left continuous. In fact, with all notation is left continuous right limit. And then we need to consider this is the canonical space. This is an increasing process with left is left continuous and the right limit. And this we can introduce a Levy metric, and we have a very much better topological structure. Okay, so this is the technical reason why we consider L hat here, and also the other reason. Okay, so this other reason is that in all the known applications of this bank algebra-based representation theorem, the optimal solution in the application of this representation to the optimization problem, the optimizer is in fact obtained by L hat. Okay, depends only on L hat. If you know the L hat, you can obtain the optimizer in the applications. So we don't really lose anything if we consider the law of L hat, because the law of L hat can also induce the optimal control. And for example, if we look at the timing, okay, for example, this is the first hitting time of L, and of course, this is the same if we consider the running maximum of L. It will give the same hitting time. It will give the same hitting time. Okay, so finally we consider more general formulation and with common noise and also in the strong formulation. Again, we stay in the strong and we fix this common noise, we fix this filtration. Okay, so I'm going to present this two approaches. So in fact, we're still, I think we almost finished. We still need to read the last time before we put on our first version on archive. We have three approaches, but I just want to present this the two first one, but the last one is very special case. It's very special. Okay, so for the first approach, we look at it as a fixed point problem. So we use the Schroeder fixed point theorem to prove the existence. Okay, and then for a second approach, we're going to use the Tarski fixed point theorem. Okay, so I just want to mention. And for another approach, for these two approaches, we have only existence. But there is a third approach. We have a uniqueness, existence, uniqueness. But the third approach requires many conditions, many technical conditions. Okay, so the first, this is Schroeder fixed point theorem. Schroeder fixed point theorem says that you have non-empty convex closed subset of Hausdorff topological space. Okay, sorry, locally compact. Okay, sorry, this this tab here. So this should be a locally compact vector space. V. Okay, and if you map us, okay, if you consider any map of K from K, and also the image of K under this map of pi, the image of K is relatively compact, and then you have existence of fixed points here. You have existence for a fixed point. So this is a short fixed point. And you need to, so what is difficult to check is that first you need to know that the image of this map is relatively compact. Okay, it's pre-compact. And also you need to make sure this map is continuous. Okay, so now we consider the non-maximum process. Okay, again, we consider a very simple setting. Okay, so now it is in the space. So in the space of increasing processes with each left continuous right limit. Okay, and we will keep this V plus with the Levy metric. And this Levy metric, we can, so this V, the space, vector space will be the space of measures on this metric, on this Polish space. Okay, this is a good space. And we consider the case without common noise. Then we can adjust to give you the idea. So in this case, we need to check the tightness, the relative compactness or the tightness of the law on the V plus. Okay, and then we know that under the Levy metric, the tightness of increasing process can be much easier to obtain. Okay, other than if we consider any optional process to obtain the tightness is very difficult. But now we consider the running maximum, the increasing process, the tightness is much easier to obtain. Okay, so now we need to find, we can find the tightness on this for the stochastic processes. This is relatively easy. And what is difficult is to find this continuous of this map pi. So we have an input of M. So M induce a stochastic process and represents this stochastic process, we obtain LM. And this LM induce a law of the running maximum process. So usually this one, we can say this continuous, we can assume this is a condition. We can assume that this reward function or is dependent on M in a continuous way. So this is easy to obtain. And this one is just, this one is the law, okay? The process maps to the law. And if we have continuity almost surely, then you will have continuity in distribution. This is very easy, relatively easy. Okay, so what is not easy is so the continuity, okay, the continuous, so applied this, is this one continuous? So somehow, if you give me a process Y, I can obtain a representation L, is this one is stable? This can, if we change a little M, can we still have the LM will just change a little? Okay, so we need a stability. And it seems that this is not given in the, so okay, somehow to obtain the continuity of this map of pi, we need the stability result of the classical Bank-Elegagris representation theorem. Okay, and this is we worked a lot on this one to obtain to understand this classical representation theorem and to obtain a stability result. Okay, so somehow this is new in the literature. We have also exchanged with Peter Blank for this result. Okay, so we need to have uniform convergence of Y if Yn converges to Y infinity uniformly, and for every L, for every fixed L, we have this L1 convergence of F, and then we can induce this convergence of L hat. we have this convergence of L hat in the L1 sense, or in probability, or in the L1 sense. Okay.
I mean, what is distance DL? What is DL?
Oh, sorry, DL is Levy metric. So this is Levy metric between, this is the increasing process. This is increasing process. So DL is Levy metric because this is there in the space of V.
Thank you.
Yeah, thank you for this one. Okay, so we can obtain, so this is a measure, you can measure the distance between two increasing processes. And this, we obtain this one. Okay, and for the application, we just mentioned that if we have convergence in the L1 sense, then when you consider the conditional distribution of Ln, you have the convergence, it implies the convergence of conditional distribution of L hat n to the conditional distribution of L hat in plus infinity. Okay, L hat infinity. Okay, so this is what we want because we want to consider the conditional distribution of L hat as my interaction term. Okay, this is what we want. Okay. We also have some counterexamples to show that we cannot relax this uniform. This is somehow quite strong. Okay, some uniform convergence distance between Yn and Y plus infinity, and we can find some counterexample. If we only have point convergence of Yn almost surely, and point convergence but not uniformly, you cannot imply this convergence in general. So okay. The other sense, we also have counterexample shows that we can only expect this convergence of running maximum, but not this process L to Lf infinity. Okay, so we cannot expect this one. So in fact, in the Bank-Lewis representation theorem, this given a process where this L is not unique. This is where L is not unique, but this L hat is unique. The running maximum is.
So, and what is the difference between L and L hat?
Okay, so L hat is the L hat. So L hat and T is the running maximum. S T of L and S is the running. So L is just has no regularity in general. There's no regularity of process L. L is just an optional process. We don't have any regularity. So we consider this running maximum to obtain the regularity of the passes. Okay. So we don't have, okay, so this is natural. Somehow this is natural to consider the convergence of L hat. And so this is also the reason we use L hat, the distribution of L hat as the interaction term, Okay, and then based on this, I think once we have this stability result, we can show that the continuity of this one, we can assume this is a condition, and this one is the stability result, and this one is very easy, it's relatively easy, because we have strong convergence of L hat, then induce the convergence of this law. Okay, the convergence. Okay, the convergence in L1 imply the convergence in distribution. Somehow is so we can obtain abstract first existence theorem, and also for this existence theorem, we remember. I just want to mention. Okay, sorry. I go back to again. In the short fixed point theorem, we need this to be relatively compact. Okay. Somehow we need the V plus. Okay, we need the L hat to be tat. We want to have some tatness of L hat. We need to have. But this. Okay. So this is also why we introduce a function of psi. Okay, so in the real theorem, the interaction term is the law of psi of L hat, is psi of L hat. And if you look at the application of this one, you will truncate. So in all the application of this one, you will truncate this running maximum. you will in the singular control, you can say that you need to truncate. And in the optimal stopping problem, this is the first hitting time for some level, for some fixed level. So again, you truncate this process L hat. Okay, so the process L hat, you don't have tightness, but after truncation, you can easily obtain the tightness of the family of process L. You truncate by the same one. So finally, this conditional law is tight. Okay. So this is our first existence result. Okay, our first existence result. I want to, our second one is we use the Tarski fixed point theorem. Okay, I just want to mention what's Tarski. Tarski theorem says that this, if you have a complete lattice, so a complete lattice with a partial order on some set. So this is a partial order, it means that not every element in this space have a order. So C1, C2 maybe it doesn't have order. But in case that if you have a order, so for itself, you have a order, okay? And if C1 is bigger than C2 and C2 is bigger than C1, then necessarily C1 equals to C2. And also if you have this C1 bigger than C2, C2 bigger than C3, implies that C1 is bigger than C3, okay? And in this one, this space is a partially ordered space, or set, or partially ordered set, okay? But this is a partial order, means that not necessarily you just have arbitrarily two elements, maybe you don't have a order. Maybe you don't have a order. But if you have a order, then this is true. Okay. And this is a complete lattice, means that for any subset of C, you can find C minus, C plus, such that any element in C in this subset is bounded between C plus and C minus. And in this case, you have a upper bound and you have a lower bound. And then in this is okay. And in this case, if you have a monotonic map from C to C, then you have a fixed point. Okay. In case that you have a monotone, okay, sorry, should be monotone map from C to C, and then you have a fixed point. Okay, so what we need to do is to introduce a partial order on this space, Okay, I don't give the details, but because it will be the state, otherwise the statement will be a little long. Okay, so somehow this partial order is very easy to introduce here, just because we can compare the V plus. We can easily compare the increasing process. If the process is higher, then we can introduce this partial order. But we don't need to, we just want this partial order. We don't need to compare any optional process, any increasing processes. We just say, if one process dominates another process, then they have a order. Okay, so this is enough. And also if the law of M1 is dominated by M2, and then Y1 minus Y2 is a supermartingale, because when you take expectation and you want to have a decreasing process somehow, and you have this order F1 bigger than F2, and then in this, under this technical condition, you can construct a monotone map. You can find a complete lattice on this space, and then you can find a monotone map from this space in the fixed point, and then you can find the existence of solution. Okay. Yes. So this is my last slide. My last slide is that, okay, the supermartingale condition. So this condition is adapted from a paper by Carmona, De La Rue, and Laker. Sorry, the type again. So in this study, the Mifflin game of timing, of course, with one population, and they use Tarski fixed point theorem to obtain the existence of fixed point. So they already have this kind of supermartingale condition. So we adapted it from their paper for this condition. Okay, so the main idea is to introduce a partial order on this space of measures and to make it become a complete lattice, and so that this is a monotonic. This is a monotonic map, and then you can find optimal existence of a fixed point Okay. And we have a third approach. So this is my last slide. I want to just mention in our paper, we have a third approach, and with more structure condition, somehow more complicated condition, and we have existence uniqueness result. But somehow it's very special, a very special case. Okay, so I don't present it here. Okay, so this is the end of my talk. Thank you for your attention.
Thank you very much. Are there questions?
I have one question, if possible. Thanks. Basically two, actually. So firstly, an economic one, as you related these two principal agent problems, what kind of PA problems could be solved in this? And couldn't they be better even solved still in the game theory context? As you discussed mean field games, and the minor one, as Levy metric was mentioned, could this in any way be replaced by another metric, say Wasserstein or similar in this case? Thanks.
Okay, so for the applications of in principal agent problem, we consider, I just check that, do I have my slides? Other slides? Yeah, this exactly, I have another slides for the exit or contracted. Maybe I just mentioned this one, the principal agent problem formulation of the, okay. So, okay, so the principal agent problem is, we can consider is here. We can consider this kind of principal agent problem. Okay, so the principal need to this is contract. Okay, there we have different agent. Okay, and the idea is to design a contract. Sorry.
But is there any special logic? I mean, could this be put also in game theory context, this agent problem that you...
I don't know.
Okay.
Sorry. Okay, I just mentioned that the problem is the application of our problem is this one. So we want to find a contract. A contract is, so for every agent to solve optimal stopping problem. This is the agent problem, and the principal want to find the optimal contract. So this is why is an exit contract, because when the agent chooses to stop at time tau and he receives this reward function. Okay, so the principal wanting to design a contract Y such that it maximizes this one, and this tau hat is the optimal stopping time of the agent.
Okay.
And in fact, for this kind of principal agent problem, you can solve by the representation theorem, because this L is universal. Because you can use a universal L to represent the optimal behavior of the agent, the optimal behavior of different agents. And this is how I don't know. Can you repeat your question? I'm sorry.
No, it is okay. I was just comparing this to the game theory context. If this could be also, but this is more economic related, actually.
Yeah. This is not. Yeah. Yes.
Okay. Thanks. The
So
second
it's different. In fact, it's different to the Murphy game. Yeah, it's different to the. It's not a symmetric game as the Murphy game, the principal agent problem.
Okay. Thanks a lot.
Are there further questions? Maybe I can ask a quick one, because in the classical representation, you had this stability result. Can you recover such a stability now in this mean field setting again?
Yes. So we use this. I would say yes in the case. So okay, what we can say is that here. So we can have, in the sense that if so for the moment we have only existence. Okay, we have a third approach to have a uniqueness, also have a uniqueness, but it's very special. It's under some structural condition. So let's assume the uniqueness. If we assume the uniqueness and this stability result, we will imply this. Yes, we will imply because this stability result means that we have some stability of L hat, and usually the optimal behavior of the agent is a continuous function of L hat. So this will imply the stability of the optimal reaction, the optimal control, the optimizer. Okay. So, so if we have uniqueness of this mean-free game, and I want to say this induces the stability of the solution of the mean-free game.
Thank you.
Okay. But in general, we don't know. But for the two-first approach, we only have existence. They show the fixed point and the task fixed point. They only give existence result. So with the additional uniqueness result, this stability induces the stability of the solution of mean-free game.
Thank you. Are there further questions? All right. If it's not the case, then let's thank Xiaolu again. Thank you for staying up so late.